an actual example of Hess's law at work. It's a relatively brief experiment. Like most of these have been relatively brief, but there's steps involved that we need to be careful about doing. There's a lot of data collection in terms of volumes and masses and temperatures and everything else, and then quite a few calculations post lab. I also put in important reading to do for this one would be to look at the lab manual. And the lab manual I've posted in Canvas. Obviously, we're not using that particular lab manual because it's we're sort of working in place right now. But there's a lot of good information in there about this particular type of experiment. In the one we're going to do today is not exactly the same as the one we were going to do in the lab. The one in the lab involved weak acids and strong acids. We're strictly doing strong acids with this one, but a lot of the lessons learned will be the same. So I want you to read that through and do the pre-lab questions. We're going to call them post-lab questions, and have that included with your report. So people had a chance to sort of look this over real quick before we get going. Has anyone had a chance to look at it before we get going? Oh man, everyone's being coy on me. I know we're almost done, but come on, we can do this a little bit longer. Who's had a chance to read the lab?
Doing that right now.
You're doing it right now. I appreciate your honesty. All right, I'll just sort of take us slowly through it, and then we'll go to the website and do it ourselves. So we've been learning about Hess's law, and I can see how some of you wonder, like, what's its real life application, and other than listen to dogs barking outside your window. One of the things that Hess's law allows us to do is to do two separate reactions, add their energies together, and be able to make a prediction of what a third reaction would be. And basically, that's what we're going to do today. We're going to do 3 different reactions, and one of them will be the sum of the other 2. So what we'll be able to do is measure the heat of each reaction, calculate what the delta H would be. And you remember what delta H means? When I say the reaction has delta H, what am I actually reporting?
Change in the temperature.
Nope.
And the heat.
The heat, but the heat.
The enthalpy?
It's the enthalpy, but what's it per? Is it for just that reaction?
Per formation?
So if I do a reaction with like 1/10 of a mole of something, and I measure the heat Q, is that the same as delta H?
It's the specific heat.
The specific heat is something different. Here, let me draw.
The overall reaction.
Wow. Could you repeat that? That kind of came out.
What was that?
Yeah, that was strange. So I'll sort of ask it a different way. So I do a reaction, and I measure the change in temperature, and I calculate Q. So remember, Q is the heat either evolved, either the temperature goes up and heat has been released, or the temperature goes down and heat has been absorbed. But I need to know the mass of whatever my reaction was. I need to know the specific heat, and I need to know the change in temperature. So that gives me Q. That's the amount of heat. So what's the difference between Q and delta H? There's a difference. They're both given in joules, but there's something more that's given for delta H.
Is it based on how the chemicals react depending on the heat produced?
I mean, that is part of it. Yeah, I mean, basically we're looking at delta H means the change in heat from a reaction, but a particular amount of reaction, I'll put it that way. Q is just given in joules. Delta H is given in joules per something.
Kilojoules?
Well, Q can be in kilojoules too. Kilojoules just means a buttload of joules, right? So they both can be in kilojoules or joules or calories for that matter. But there's something specific about delta H. When we refer to delta H, it means something slightly different.
If it's exothermic or endothermic?
Nope, that just says whether or not the sign is going to be positive or negative. And Q can be positive or negative too. Let me put it a different way. If I do an experiment, let's say I do an experiment with 0.1 mole of A and B, and I make C, and you do an experiment with 0.2 moles of A and B, and you make C. When I report the amount of heat given from my reaction, I'm going to report the amount of heat Q. You're going to report the amount of heat Q. What value of Q is going to be larger? The first reaction or the second one? So if this is the first reaction and that's the second
The
reaction.
value.
Yeah, someone needs a faster computer or a quicker internet. Couldn't make that out, sorry. Reaction 1 or reaction 2, which one's going to have a larger value for Q? The one with one with 1/10 of a mole of A plus B, or the one with 2/10 of a mole of A plus B?
The second one?
The second one. Yeah, because it's got more. It's got more stuff. There's going to be more things reacting. More C is going to be produced. If it's an exothermic reaction, it's going to release twice as much heat. If it's an endothermic reaction, it's going to absorb twice as much heat. So this value of Q is going to be larger. But we both did exactly the same reaction. We both did A plus B and we got C out of it. We both did exactly the same reaction. So our delta H reaction should be the same. How is that? How can we both get the same delta H? Second value of Q is going to be twice as much as the first value of Q. But the delta H reaction is going to be identical. How is that possible? And you guys got a test coming up on this soon.
It's related to delta H formation.
Yeah, it will be the delta H formation of C. That will be the delta H formation of C. But why is it the same? I did the experiment, you did the experiment. You got twice as much heat as I did, but our delta H is the same. How's that possible?
Because the energy that I need to break down the bond is equal to the energy that I need to make bond.
Yes, we both did the same. We both did exactly the same experiment. You just did the second experiment, we just had twice as much stuff. And so there was twice as much heat involved. So your value of Q is twice as much as mine because I only used half as much stuff. But when we calculated our delta H for the reaction, it was identical. Why is that?
Because it's the quantity that matters.
Which quantity? Yes, it is the quantity that matters. So delta H is given in kilojoules per what?
Gram?
Per gram?
No. Remember, it's a reaction. It's a chemical reaction.
Mole.
Mole, there you go. Yeah, delta H is always kilojoules per mole. And the reason for that is, yeah, if you do the experiment, I do the experiment, Ilham does the experiment, Casper, Sandy, they all do the experiment. We all use different amounts. We all calculate different values of Q because it's going to be different amounts of heat given off. But the amount of heat per mole should be exactly the same. And so that's one thing you're going to be calculating today, because you're going to be, that allows us to compare one reaction to another. They all should, if we're all doing the same like acid-base neutralization reaction with the same acid and the same base, we should all get the same amount of heat per mole. And that's one thing we're going to be doing today. We're going to be calculating Q, and for Q, you do need the mass. The reason we need the mass for Q is because we need to know the heat capacity. And heat capacities are given in grams per gram because it's based on mass. How much mass was there that absorbed that heat? How much mass was that heat taken from? So we do that in mass to figure out just the heat part. But when we're thinking about how much a reaction, when we're talking, anytime we talk about reactions, we're talking about moles, because remember, moles react, grams don't. You know, moles balance, grams don't balance. So we're going to be calculating Q for the heat and delta H for the reaction. And when we put these things together, the delta H's should balance out, not the Q's, unless you're using, because I can have Q from one reaction and a second and a third reaction. If they're all different amounts, I won't be able to add them together using Hess's law. If I have delta H, it's going to be per mole, and I will be able to do that. So let's look at the reaction we're going to be doing today, or reactions. So it's 3 reactions. So here are 3 reactions we're going to do. The first one is just dissolving sodium hydroxide in water. So is that a chemical reaction or a physical reaction?
Physical,
Okay. Explain.
because you're not changing the chemical compound of it, you're just dissolving it.
Interesting. I would agree with you if I was dissolving like sugar in water. The sugar doesn't really change. You're not breaking any bonds between the atoms in the sugar molecule. But what about sodium hydroxide? Are we actually breaking any bonds?
Probably the sodium bonds.
What sodium bonds?
Sodium hydroxide bonds.
What kind of bond is that?
Heat is being released, so that could show that it's chemical.
What kind of bond is it? Remember that we have basically two types of chemical bonds we've
Covalent?
studied so far. Covalent and what's the other one?
Ionic.
Ionic. So which one do we have here?
Covalent.
Do we have two nonmetals?
Sodium is a metal, so it's a ionic, sorry.
Sodium is a big time metal. And we get charges out of it. Remember, we get a sodium plus and an OH minus. And so I can see the confusion, because when they're in the ionic bond, they're also charged, right? I mean, they're two ions, but it's this interaction between them, the positive and the minus charge of the two things, which keeps them together. That's an ionic bond. And so we're actually breaking it. So it's different in the fact that when we break a covalent bond, there's electrons that were shared, and then we break that so that they're no longer sharing those electrons. Well, in this instance, they weren't sharing electrons before. Hydroxide just took the electron from sodium, but there was a strong interaction between them. And you remember, it's an electrostatic interaction. Static meaning that the electrons weren't moving. The electrons were negative in one place and positive in another place. So they weren't moving, but that's a very, very strong interaction. And then we form new bonds when the sodium, and we're going to get to that in the next chapter. I'm just going to briefly go through some of the next chapter because it explains a lot of this stuff. When the sodium goes into the water, it then forms bonds with water. Not covalent bonds, but something we're going to learn about called ionic dipole bonds. So we have an ion and a dipole, and they interact with each other because you remember our oxygen in water is slightly negative, and the hydrogens are slightly positive. So while the sodium is going to be interacting with the slightly negative part of water, the hydroxide ion is going to be interacting with the slightly positive part of the water, which is the hydrogen. And that's a very special kind of bond called a hydrogen bond that we're going to sort of introduce you to. So we're breaking an ionic bond, and we're forming both hydrogen bonds and ion dipole bonds. And they're both very, very strong. Not quite as strong as covalent bonds, but pretty strong. And so whenever you break bonds and form bonds, that's a chemical reaction. So that is actually a chemical reaction taking place. And we're forming bonds and we're breaking bonds. And so there's going to be heat involved in that. And we'll see that it's actually an exothermic reaction. Because you see, which side is the heat on? Is it part of the reactants or part of the products?
Reactant.
Product.
Yeah, the heat's on the product side. So it's on. So here's our arrow. And so we've got heat on the product side. We're going to make, when we dissolve the sodium hydroxide in the water, it's going to make sodium ions, hydroxide ions, and it's going to release heat. So that's our first reaction. So we're just basically, then we're going to calculate Q for that reaction. So Q1. Our second reaction, we're going to take also solid sodium hydroxide, and then we're going to add hydrochloric acid to it. So this reaction is going to be solid sodium hydroxide plus H plus CH minus, because those are already in solution. Remember, this is a strong acid. And when we put a strong acid in solution, it's already going to be converted to H plus and CH minus completely. And so this reaction will then be releasing, breaking this ionic bond again, to doing the same reaction, breaking that ionic bond, forming sodium and hydroxide ions. The sodium ions are just going to stay in solution. The chloride ions are just going to stay in solution. But the H plus and the OH minus ions will form water. That's a neutralization reaction. Remember, that's a neutralization reaction. We have a strong acid, H plus, we have a strong base, OH minus. When they come together, they neutralize each other and form water. And that's also an exothermic reaction, because we're breaking bonds and we're forming bonds. And so the net is we're going to be releasing heat from that reaction. And so the third one, instead of taking solid sodium hydroxide this time, we're going to take a solution. So this time the sodium hydroxide is already in solution. So I already have my sodium ions and my hydroxide ions. And then we're going to use the same strong acid. So I'll have my H plus, my Cl minus there. And basically it'll be the same reaction as the last one. We'll get the same products as the last one. Sodium ions, chloride ions, and water, and some heat being involved. Now, which of these two reactions can be added together to get the third one? We're dealing with Hess's law here. So which two of these reactions can we add together to sum up to get the third one? Think about it this way. In two of the reactions, we're doing one thing. And in one of the reactions, we're doing two things. Which one are we doing two things? And can we add up the other two reactions to add up to that?
The first one?
What about the first one?
Mm.
Or are you just answering the question, which one has two different reactions happening?
Mm-hmm.
One of the reactions has actual two separate reactions. The other two are just single reactions. So which two can we add together to get the third?
The second reaction.
What about it?
Since there is NaOH and
No, I've asked too many questions. I've confused myself. So which question are you answering?
So the reaction 2 will be similar to reaction 3 because of the products being on the same side.
Right. Okay. So that means I can add 2 and 3 together and get 1?
One is you put the products on the other side. You have to flip it to get reaction 3.
Okay. But if I flip it, I don't have solid sodium hydroxide in reaction 3 anywhere.
But wouldn't it cancel out in reaction 2 when you use reaction 1?
So which two?
Reaction 1 and 2 will cancel out, right? The NaOH, sodium hydroxide.
If I move them around, yes.
Yeah, you just have to have the reactant on the product side for reaction 1.
All right. So which two reactions am I adding together?
1 and 2 to make 3.
Don't know about that. Look at it this way. Which one? Because I think one of you got it right, but let's just look at this one question first. Which one of those reactions is actually two reactions happening at the same time?
The product of 2 and 3 is like the same.
Mm-hmm.
So would it be 2 and 3 make 1?
Well, which one of the reactions is actually two reactions at once? I'll put it that way.
The second one?
Yes, the second one is actually two reactions, right? The second one has both solid sodium hydroxide dissolving in water and being neutralized by the hydrochloric acid. So it's actually two reactions. So reaction 1 is just the dissolving of the sodium hydroxide in water. And reaction 3 is the sodium hydroxide ions that are now already in solution being neutralized. So actually what we're doing, if we add reaction 1 plus reaction 3, we'll get reaction 2. Because reaction 1 and reaction 3 are both parts of reaction 2. So what we should be able to do is measure the heat from reaction 1, Q1, and the heat from reaction 3, Q3, and we add them together, we should get the heat from reaction 2. Because reaction 2, both of those things are occurring. Both the sodium hydroxide is being dissolved in water and creating ions. That's reaction 1. And then subsequently, those ions are interacting with hydrochloric acid, undergoing a neutralization reaction and forming water. So both of those reactions are number 2. Both 1 and 3 added together equal 2. So that's what we're going to do today in the virtual lab. We're going to do the first 2 reactions and the third one and see if we subtract, basically if we subtract Q2 from Q1, will that equal Q3? Which is the same thing as saying if I add together Q1 and Q3, will I get Q2? Okay? So then, we'll do these 3 reactions. We're going to do them in little cute little styrofoam cups. And we're going to calculate how much heat is evolved using our old friend Q equals Cp, and we're going to be doing it in water, so we're going to be using the specific heat of water times whatever mass of water we're using in our reaction times whatever change in temperature we see for each of the 3 reactions. Then we're going to convert them to how many moles of sodium hydroxide were dissolved, how many moles of sodium hydroxide interacted with HCl, how many moles of water was produced, and then convert. So then we'll convert Q to delta H reaction, and see if we can add our delta H's together. Okay. So let's just go to. So here's where we'll do. Here's where we'll put in our data. We're going to do the 3 different reactions. Each one of them is going to involve a different amount of sodium hydroxide. Either we're going to have solid sodium hydroxide and we'll look at a mass, or in the third one where we already have sodium hydroxide in solution, we'll just calculate how many moles that is based on the volume times the concentration. Volume times molarity equals moles, right? Since molarity is moles over volume. So calculate the number of moles, take the temperature of the solution before we do anything, see what the final temperature is, get our delta T, calculate Q for that particular reaction, and then calculate delta H, because we need to know how much heat was involved per mole. And we're going to do it with different amounts. So I think they suggest the second amount use twice as much material. So your Q should be twice as high, but your delta H should be exactly the same because you're dividing it by the number of moles. Okay. So shall we go to any questions about that before we get started?
No.
Everyone's gung-ho to get going. All right. So what we'll do is we'll go to the site. So everyone's seen this site?
Yeah.
Yeah.
And then, I don't think there should be a problem with Macs and PCs. I'm kind of keeping my fingers crossed. I don't think there is. Let's do that. Let's. All right, do you see the screen for heats of reaction?
Yes.
Okay, good. All right. All right, so let's look at our procedure. So it says we're going to take out a 50 ml graduated cylinder and a foam cup. So we're going to go to glassware, take out graduated cylinder, 50, there we go, and a foam cup. Let's see where the foam cup is. Is that under tools?
It would be under glassware. Other.
Oh, I can't. Oh, there it is. Oh, yeah, I need to move it around a little bit. Okay. Yeah, I can't get it all on in one screen. Foam cup, so cute. Okay, there's my foam cup. So, going to put 50 mils of water. Solutions, water. So put 50 mils of water in the graduated cylinders. Let's drag it over there. So precise, I want 50 mils. So 50.0 mils. Pour. So you can see I've got 50.000 mils, so pretty accurate. And then I transfer that to my foam cup. .0 pour. Okay. So, and when you click on the cup, you see it gives you the temperature. Okay, so the temperature, so this is our initial temperature, 25.00 degrees. So we should have a fairly accurate temperature. So 2500 degrees. Another thing you can notice is it also gives you the concentration of H plus and OH minus. So what would be the pH of the water right now?
Seven.
Yeah, 7, because we calculate the pH based on the concentration of H plus. The concentration of H plus right now is 10 to the minus 7 moles. And so we take this, take the negative of that for the pH, and so it's pH 7.0. And this will change radically when we put our sodium hydroxide in. So now we want to get, I'll put the water away for right now. Remove. So I want to scale. I want a weigh boat. I'm going to put my weigh boat on there. So you remember when you put the weigh boat on top, what do you have to do in order to get the balance back to 0?
Press tear.
Yeah, press tear. Now when I put the sodium hydroxide in, I'll get the accurate mass. So I guess under solutions I'm going to have here we go, strong bases. Solids, here we go. So solid sodium hydroxide. Oops, where'd my sodium hydroxide go? Oh, it's over here. So I put it up here, and valid amount. Let's say 0.9. So I get 0.9 grams. So pretty much somewhere around a gram. As long as it's an accurate mass, it doesn't really matter. Somewhere around a gram. Could be a little bit more, could be a little bit less. So I take my sodium hydroxide and I add it to my foam cup. Just put it in there. And I just say, now put my 0.9 grams in. All right, now when I click on the foam cup, look what's happened to the temperature. So with 0.9 grams of sodium hydroxide, my temperature now has gone up to 29.77 degrees. And look at my concentration of OH minus. It's like through the roof now. So what's the pH of my solution now?
13.5.
What is it?
13.
13.5.
It's going to be around 14.
Oh.
Yeah, 13.5, something. Oh, it's written down there. Yeah, I was just going off the concentration. Of course, I was just going off the concentration of sodium hydroxide, of H plus. Sorry. Yeah, you can see that if you take the concentration 3 times 10 to the minus 14, that's around 10 to the minus 13 and a half. And so that is the pH, is 13 and a half. So that's our first reaction. So how do we go about calculating Q for this? How are we going to calculate Q?
Are we going to use the specific heat of water?
We sure are. So take me through it. How are you going to calculate Q for that reaction?
So 4.184.
Okay, so Q is going to be 4.184. 4.184 what?
Joules
There you go.
over grams per Kelvin.
Yep. Or delta C or degrees C, same thing. Times, so what's my mass?
Would it be 50?
It would be 50 because we're going by the specific heat of the water. Obviously, we added another 0.9 grams of sodium hydroxide, but that's not water, is it? No, we're going by the mass of the water. So you're absolutely right. That is 50 grams because 50 mils is 50 grams. And what was our delta T?
It would be 4.77.
Yes, 4.77 degrees. Where is my calculator? Uh-oh. Someone's going to have to do the calculation for me. My calculator's missing. Shice, where did it go? Can someone do that for me while I look for my calculator?
It would be 997.884.
997 point, what was it?
884.
884. 884 what?
Joules.
Joules. Okay. Yes. How are we going to convert that to delta H? Because that's really what I want. I want delta H. And what was delta H again?
Delta H is Kelvin, Joule over mole.
Kilojoules, not Kelvin joules, kilojoules or joules. It's just joules divided by moles. That's all it is. So moles of what? What are my moles of water? What?
Of
NaOH.
Moles of NaOH, because that's my reaction, right? My reaction is this. My reaction is solid, goes to H plus and OH minus, both aqueous. That's my reaction. And so I need moles of sodium hydroxide. So how many moles of sodium hydroxide did I have? Somebody help me out. How many moles of sodium hydroxide? So it's going to be delta H is going to be joules. It's going to be basically it's going to be my Q divided by moles of NaOH. That's what my delta H is going to be equal to, right? But how many moles of NaOH did I have? How am I going to calculate that? Man, if you guys can't calculate moles to grams to moles and moles to grams by now, bad news coming.
You would multiply 0.9 grams
There you
times
go.
1 mole over the molar mass, which is 39.997.
So proud of you. Excellent. That is correct. 1 mole of sodium hydroxide. And the nice thing for you guys, you can just look that stuff up. You know, you don't even have to calculate it like a real chemist would. Actually, a real chemist would just look it up. Yes, that's how many moles you have. So how many moles of sodium hydroxide did we have?
0.022501687.
Hang on. Oh man, you're the queen of significant digits. So 0.02, and then go slowly. Remember, I'm old and feeble. So 0.2 what?
250168.
I think that's probably enough. Here we go. Yeah, so that many moles. So what's my delta H?
Divide the joules by the moles.
Yeah, I divide my, well, which joules? What joules?
997.
I divide my Q. Remember, this is Q. Q is equal to 997.884, then yes, I'm going to divide that by 0.0225017, and I'm sure there's another 16 digits, moles. That's going to give me my delta H. So what's my delta H going to be? Delta H reaction.
Four, 47.04933.
Joules per mole.
Yeah.
Or what's another way we could, what's probably a shorter way to put that? Instead of having all that numbers, all those numbers, what could I shorten that to?
Scientific.
No, not just scientific, but I could, if I wanted to put that in kilojoules per mole, how many kilojoules would that be?
You multiply by 1,000 over 1,000 kilojoules over 1 joule.
It's the other way around. There's 1,000 kilojoules in 1 kilojoule. So the opposite. So I would multiply that by 1 kilojoule is 1,000 joules. So basically I would move my decimal place 3 places. 1, 2, 3. So 44.35 kilojoules. So that's the amount of it. That's a lot of energy. That's the amount of energy released just by dissolving a mole of sodium hydroxide in water. So that releases a lot of heat. So that would be our delta H for reaction 1. 44.35 kilojoules. So let's do reaction 2. Let's go back to our heater. Let's go back to the lab. All right, so now we want to do reaction 2. So now we're going to also use solid sodium hydroxide, but this time we're going to add HCl to it. So I'm going to take my foam cup and empty it. Remove the liquid. Oh, it's still warm. All right, I'm going to get rid of it then. Remove. Okay, gonna have to get a new one. Put that back up there. I think I'll just use the same. Actually, I could use a different. I'll use like a gram this time. So 1.00 grams. Okay. Now I'm going to get my glassware, other. I want my foam cup. There's my new foam cup.
Professor, I keep
Yeah.
pressing tear, but it won't reset it.
Oh, okay. It won't really? If you
Yeah, I'm
if
pressing
you,
tear.
Oh yeah, it won't. I guess it's probably if you removed it and then put a new balance on, it would do that. Yeah, just take it off the desktop and then just put a new balance on. Yeah, I basically recycled the whey boat. And I put 1 gram in it. So I got my 1 gram of NaOH. Now I'm going to look for HCl this time under solution. So that's going to be so HCl, is that a strong acid or a strong base?
Strong acid.
Strong acid. Yes, indeedy. So here it is. So we want half molar, not 1 molar. We want half molar, okay? So take my half molar out. Put 50 mils in. See that I got 50, okay? Now I'm going to transfer my 50 mils into my foam cup. Put 50 in there. Now have a look at the, oops. So now look at what the concentration of H plus is. It's the same as the concentration of HCl, right? That tells us it's a strong acid, because that tells us that with the HCl, all of the H plus and the Cl minus have ionized. So whatever the concentration of acid is, that's going to be the concentration of the H plus. And that's basically how we determine whether something's a strong acid or a weak acid. If it's a weak acid, the concentration of the acid will be higher than the concentration of the H plus. Like if you have like a weak acid, like acetic acid or citric acid or something like that, the concentration of H plus could be much less, like hundreds of times less than the actual concentration of the acid. But with something strong like HCl or sulfuric acid, H2SO4 or HBr, something like that, or nitric acid, all of it ionizes. So let's make a note. So we've got half molar HCl, and our temperature, again, is 25 degrees C. So now we're going to take our gram of NaOH and put it in the cup. So 1.00. And wow, look what happened to the temperature. It went way up this time. So it went from 25 to 3697 degrees. So a lot higher than the last time. All right, so let's go back to our workshop and calculate Q for this reaction. All right, let's clear this off. So this time, let's write down what we've got here. So we've got our half molar HCl, and we have 50 mils of it. So we should figure out how many moles that is. Because one thing we want to figure out, because when we figure out our delta H, our heat of reaction, we're going to need to know how many moles we're talking about, right? So basically we need to know which one is in excess. Is it going to be our NaOH or is it going to be the HCl? Because whichever one is limiting, that's the number of moles we're going to use. Did you understand why that is? Because this is my reaction, right? I've got HCl plus NaOH makes NaCl and water. So really what I'm looking for is the neutralization reaction. I'm looking for that. I need to know how much of the water was produced. And so I need to know how many moles of acid and base were neutralized, and then figure out which one was more, okay? So what's going to be our moles of HCl? How are we going to figure that out?
From the molarity?
Mm-hmm. So my molarity, what is molarity? What is that equal to?
Mole over liter?
Right, so it's 0.5 moles over 1 liter. So what do I multiply that by?
1,000 because ml.
Why am I multiplying it by 1,000? I didn't use 1,000 liters.
I have 50 ml, so I
Right.
want to, yeah.
Right. So how many liters is that? That's what I need.
0.05.
Yeah. 0.050 liters. So I divide this by 1,000 because there's 1,000 mils. Actually, I don't divide, right? I multiply by 1 over 1,000. So that's how many liters I have. So how many moles is that?
Zero point zero 0.025 mole.
0.025 moles of H plus. Now, how many moles of OH minus do I have? How am I going to calculate that? So what form did I add the OH minus? Was it in a solution or was it a solid?
Solution.
I added the HCl, I added the acid in a solution. How did I add the hydroxide?
Solid.
What was the solid?
NaOH.
Which is what? What is that? What do we call this?
Base.
Sodium hydroxide.
Sodium hydroxide, right. So my base is sodium hydroxide. I added solid sodium hydroxide. So to figure out the number of moles of hydroxide ion, I need to figure out how many moles of sodium hydroxide I added. So what was the mass of the sodium hydroxide I added? Do you remember?
1.0 grams.
Yes. So I added 1 gram, and I need to convert that to moles, just like we did the last time. How many moles of sodium hydroxide did I add? What's my molar mass of sodium hydroxide? Was it 39.99 something?
39.997.
997. There we go. Right. So how many moles of sodium hydroxide do I have? Hey, Slidgy.
0.025.
0.025001887.
Not that much, Professor, numbers.
So yeah, so pretty much exactly the same. So it's pretty much exactly the same amount. So we could use either one. So basically we can use 0.0025. That's how many moles we had. So we can use that. That's the number of moles we're going to have, right? So let's calculate Q. What is going to be our Q for this particular reaction? So remember, for Q, how do we calculate Q again?
Specific heat
Mm-hmm.
times mass times change of temperature.
Right. So what's our specific heat?
It should be the specific heat of HCl.
But what's But HCl is a solution. What's it a solution of? It's a solution in
Water.
say, water. Yes, it's dissolved in water. And so the amount of HCl versus the amount of water is minuscule. So, I mean, just figure out the molarity of water. It's much, much higher than 0.5. So basically, it's 99.9% water. And so we're just going to use, but you're absolutely right. In a way, we really should figure out what the heat capacity of 0.5 molar HCl is. But it's not going to be very much different from water because it's pretty much water with a small amount of something in it. So we are going to sort of cheat a little and just say that it's the same as water, but it might be slightly different. But it's going to be pretty similar. What's going to be my mass of water?
Would it be 50?
Mm-hmm. Yeah, because we had 50. So again, this is going to be a slight approximation because we had 50 milliliters of the 0.5 molar HCl. And again, we're sort of assuming that the density of that, well, actually it doesn't matter what the density is because we're looking at the mass of the water. And so we're assuming that it's 50 grams of water. It's not going to be exactly 50 grams of water, but pretty darn close. So again, this is going to be an approximation, 50 grams of water. And what's my delta T this time? It's a lot more, right? What is it?
11.97.
11.97. Yeah, it went up big time. All right, so what's my Q this time?
$2505.9195.
So slowly. I am old and brittle.
2505.9195.
Really? It should be more than that, shouldn't it?
Oh, really? Let me calculate that again.
I got 2504.124.
Oh, right. No, I was good. No. You're right. Yeah, sorry, I was thinking of per mole. I was already doing the per mole thing in my head. All right. Yeah. So 2505 joules. That's close enough, right?
Yeah.
I know it's not for our sig fig monster out there, but yeah, that's pretty close. So 2505 joules. Now that's Q. What's going to be delta H reaction?
$100.1573.
So how'd you get that?
I multiplied 2504.124, which is the Q, over the moles of NaOH.
Which is 0025, right?
Mm-hmm.
So how much? So basically we're multiplying it by 40. So what is it? It's over 100,000, right?
Yeah, it's 157.348.
7.34. All right. Joules per mole. Remember, it's always going to be in joules per mole. So basically, how many kilojoules per mole is that?
Then you have to multiply that by 1 kilojoule over 1,000 joules.
Right. So our delta H reaction is going to be like 100.16 kilojoules. So 100.16 kilojoules. So Our first reaction was just the sodium hydroxide dissolving in water. That gave us a delta H reaction of 44 kilojoules. Our second reaction was both the dissolving of sodium hydroxide in water and its neutralization by HCl. And our delta H reaction was 100 kilojoules. What do you think that the neutralization reaction by itself, sodium hydroxide plus HCl, what do you think the delta H reaction for that is going to be? Based on what we discussed earlier. Let me go back to the oops. So remember, here's our first reaction. So here's our first reaction. Oh, damn it. Come on. Draw, draw. Nope, it's not drawing. Why won't it draw on the screen like I asked it to? What screen are you guys seeing? Are you seeing
lab.
the? Oh, you are
The
seeing the
PDF
lab.
file.
You're seeing the
Like
PDF
the-
file.
Yeah.
Oh, okay. Yeah, this new computer I've got has two screens, and it's confusing. All right, cool. So I was looking at the wrong one. All right, so here we go. This is weird. I get looking at two different screens. I'll get used to it eventually. All right, so our first reaction was this one, right? So we dissolved the sodium hydroxide in water, and we saw that our delta H reaction for that one was 44 kilojoules. It's not going to be minus 44 or plus 44.
Minus.
Minus, you're right, because it released heat. And then we just did our second reaction, that one. And our delta H for that one was 100 kilojoules. Now, is that going to be negative or positive?
Negative.
That's also going to be negative because the temperature went up. It released heat into the water, so it lost energy. So what is going to be delta H for reaction 3 based on those two numbers?
Around 56.
Plus 56 or minus 56?
Minus 56.
You're right. Yes, exactly. That should be around minus 56 kilojoules per mole. Because reaction 2 is both reaction 1 and reaction 3 added together, because we've got two chemical reactions happening. In reaction 1, we did the first one. We did the dissolution of NaOH in water. The second reaction is both the dissolution of NaOH in water and the neutralization reaction. And the third one is only the neutralization reaction. So, it'll be harder than it looks. We should add 1 and 3 together and get 2. I'm not going to flip you off with the number 2. Anyway, so yeah, so we should take 1 and 3 and add them together and get 2. Okay, because that's what Hess's law says is going to happen. If we take two reactions, if there's one reaction that's actually two taking place at once, we can break them down, add them together, and we should be able to add their heats together. So let's see if we can do that, okay? Let's go back. Let's me clear this. Let's go back to let's go back to the reaction. Okay. So are we back to our reaction to the simulation? Is that what you're seeing?
Yes.
Okay.
Yeah.
Good. All right. Good. All right. So now we can get rid of that. We're not going to use solid sodium hydroxide this time. Let's remove that. Let's get rid of our foam cup because it's hot. And then so for the third one, we're going to use sodium hydroxide in solution and HCl in solution. So I've got my HCl in solution here, so I'm going to keep that. I'm not going to need a weigh boat this time, so I can remove that. I will want another solution. So now I want sodium hydroxide in solution. Do I want a strong base or do I want a strong acid? Sodium
Base.
hydroxide, base or acid?
Base.
Base, very strong base. It's all about that base. Okay. So notice I've got 1 molar NaOH. So actually I want 1 molar sodium HCl. So I'm going to remove that. So I want, I want my base and acid to be the same. So I'm going to get 1 molar. There we go. So I've got 1 molar strong acid, 1 molar strong base. Get my foam cup from the stock room, glassware. There's my foam cup. Okay. So this time I'll add equal volumes of acid and base. So I think that the recommendation is 25. I'm going to put 22.5 because I'm like that. So 22.5. That's my HCl. So I'm going to put that in the cup. 22.5. Pour it in. Then take my hydroxide, 22.5. I put the same volume in because then I won't have to worry about figuring out which one is. If you have the exact number of moles, exact same number of moles, you don't have to worry about which one is limiting because they're both the same. So put that in there. Now notice everything was at 25, right? My acid was at 25, my base was at 25. So my initial temperature I can put down as 25. They're all going to be 25 degrees. All right, so now when I put in my sodium hydroxide, I will watch and see what the temperature goes to. So 22.5 mils, pour that in. And the temperature goes up to 31.67 degrees. 31.67 degrees. Okay. So let's calculate our Q, calculate our delta H reaction. All right, let's erase all this nonsense.
Professor, I have a question. So
Yep.
for reaction 3, we won't have in the table NaOH mass would be 0, right?
You put in moles, yeah. You can just skip mass because you don't really care and just go right to moles.
Okay, thank you.
Yeah, that's what we're going to do now. So you guys are going to do the same reactions twice with like different amounts. But let's figure it out. So let's figure out Q first. So Q, you should know by now that it's going to be our CP times mass times change in temperature. So we're still using water because even though we have 1 molar solutions of sodium hydroxide and water, still 99.9% of that is water. So we're dealing with water. So 4.184 joules per gram degrees C. What's my mass this time?
45 grams.
Yeah, I had 22.5 twice, so my mass is going to be 45 grams. And again, that's an approximation. It's not going to be exactly 45. It's probably going to be a little bit less because some of that mass is going to be acid and base, but most of it's going to be water. And then this time, my delta T was what?
6.67.
Yeah, it was 6.67 degrees C. So what is my Q?
1255.8276.
You sure there's any more numbers? I gotta get you a calculator that has more digits on it. Like 15. You're gonna go crazy.
Oh no.
It'll take you forever to get your work done. All right, yes. So that's my Q. That's my Q for this particular reaction. Now your Q is going to be different when you do the reaction. It's going to be different because you're going to be adding different amounts. You can add 15 of each. You can add 20 of each, 25 of each, 50 of each if you want. I don't know how much the foam cup holds, but I think it's probably at least 100, maybe more. It doesn't matter as long as your Q will not matter. It's your delta H should be the same. So what do I put down for moles this time? How many moles? See, that is going to be confusing because we have moles of this is our reaction, right? We got moles of H plus and we got moles of OH minus, and they make water. So do I count moles of H plus? Do I count moles of OH minus? Moles of water produced? Moles of H plus plus the moles of OH? Which one do you think we're going to use? So it's either going to be the moles of this or the moles of this. And remember, that's the same because we added the same volume and the same concentration. Or the moles of OH, of H2O produced, which will also be the same. Or do we add A and B together? Do we add those two together?
Add together?
Why do you say that?
Because H2O, it's about H and OH.
Mm-hmm.
So you have to add it together to get H2O.
Yes, but we didn't make 2 moles of H2O, did we? We only made 1.
Mm-hmm.
So I had 1 mole of H plus, 1 mole of OH minus, and I made 1 mole of water.
Mm-hmm.
So should I add the moles together or just use moles of acid equal moles of base equal moles of product? Well, think of what we've done in the previous 2 experiments. Basically what... Go ahead.
Would you use moles of OH?
Yeah, moles of OH, right. Because basically all these reactions, we've looked at moles of OH dissolved in water. We've looked at moles of OH neutralized. And so we're still doing that. We're still looking at moles of hydrogen, of hydroxide neutralized. Luckily, that's also the same number of moles that there is of acid and the same number of moles of product produced. So we're just looking at the moles of hydroxide, which is the same as acid, which is the same as moles of product. So moles of hydroxide. How many moles of hydroxide did we have? We had 22.5 mils of a 1 molar solution. So how many moles of hydroxide is that? How do we calculate that? Someone help me. How do I calculate that?
1 molar of the solution over 1 liter.
1 mole, right? 1 mole of hydroxide over 1 liter multiplied by what?
Multiply by 0.0225
Yep.
liters.
Remember, there's 1,000 milliliters in 1 liter. So 1 milliliter is going to be a much smaller number. It's going to be 1,000 times less than a liter. So basically, we're multiplying this by 1 over 1,000. And if you ever wonder if you got it right, just move it 3 places. 1, 2, 3, 22. Yep, that's right. Just you go back and forth 3 decimal places. So 0.0225 liters. How many moles is that? Well, 1 times that is 0.0225 moles. That makes it pretty easy.
Mm-hmm.
Having a 1 molar solution makes your math pretty straightforward. All right, so now what is my delta H reaction?
You have to divide.
Got to divide what?
0. What's that? 22.5. Oh wait, no. Sorry.
Remember, delta H reaction is equal to Q divided by moles. So what?
Was it?
You have to divide 1255.8276 by 0.0225 moles.
Yep. So what's that?
55,814.56
joules per mole. And so kilojoules per mole, it would be 55.81. So 55.81 kilojoules per mole. And so whoever said it was going to be around 56 kilojoules, good work. So you can see that they add up. Now, remember, it's not going to add up exactly because we've made some we've done some deviousness with the math here. We've assumed that we have a certain mass of water when we probably don't. So that is going to change our results slightly. But you can see it's really, really close. So what we're looking for is we want you to do these reactions twice, once with a smaller amount and once with a larger amount. So I don't think you want to go much past a gram of NaOH. If you use more than a gram of NaOH, you're going to need more HCl to react with it, more than 50 mils. Just remember that. You can use more, just use more than 50 mils of HCl to neutralize it. Or calculate which one's the limiting reagent. All right, so is everyone clear on how we're going to do this experiment?
Question.
Yeah, go ahead.
For each reaction, we're always going to be calculating the moles of OH, right?
Yep.
Got it.
Yep.
Thank you.
Yeah, because we're dealing with because that at the end of the day that those are the reactions we're doing. We're looking at because we can't add for the neutralization reaction. It won't matter because the number of moles of H plus and OH minus will be the same if you use the same volume. If you don't, if there's an excess of one or the other, go with the limiting reagent. But if you use the same volume at the same concentration, it won't matter which one to use. But yeah, generally what we're doing is we're following the hydroxide, seeing what happens to it. It's being formed in solution, and then it's being reacted with H plus to form water.
For reaction one,
Mm-hmm.
I noticed that you put 0.9 grams of NaOH instead of 1. I just wanted to understand what was your reasoning for that.
Oh, just because it said add around 1. So the instructions were to add around 1. So I added around 1.
So would it be okay if we did exactly 1 or no?
Yeah, it's fine.
Okay, thank you.
Yeah, you could add more than that if you want. Just remember when you do the second reaction, I think it's important to have less than 1, because when you add the 50 mils of the dilute HCl, if there's any more than 1 gram in there, it won't neutralize all of it. So if you're assuming that all of it gets neutralized, it won't.
So, Professor, I want to ask you, the result for the first and like each reaction, it should be have at the end similar result? Because you mentioned that reaction 1, I have to do it twice.
Mm-hmm. But different amounts, yeah.
Yeah, and the final result, it should be similar?
Your Q should be different, and your delta H reaction should be the same.
Okay.
Yeah. If not exactly the same, pretty close.
Okay.
Because remember, that's the whole point of calculating delta H, is so like if you do a reaction and I do a reaction, and 30 other people do the same reaction, all with different amounts, we should all be able to compare our results and be able to say what the amount of heat evolved from that reaction is. Because if we all gave a value of Q, they'd all be different, even though we're all doing the same reaction. So does anybody else need any help on how to actually do the experiment?
I just have one question. How you measure the weight in the first reaction of the solid sodium hydroxide? Can you show me again from
Sure. Let's go back to just to measure mass. Pull out a
tool.
Balance. Oops. Just double click on the balance of the scale. Oops. I got 2 of them. Just want 1. And then
But it's not 0 for me. When I click it, it's not 0.
Well, remove it and then put a new one on. Because I think what happens is if you weigh something, if you put the weigh boat on it, and that's under glassware, other. So when you put the weigh boat on it,
Okay, got it. And then
it remembers that mass. So yeah, just get a new one. So now when you hit tear, it should go to 0. Come on. Or it won't.
that's what happened to me.
Huh. Oh, maybe, it freaks out sometimes if you have too many things on the, if that's the case, yeah, then you just subtract 4.7334 grams. Or actually, I think you can probably just get the solid and just add it directly and just bypass the scale altogether, really. So I think that's like one of the dirty little secrets. If you want to do these things in a hurry, you don't even need to use the scale or the graduated cylinder. I think you can just pour it in and say exactly how much you want. But yeah, that's strange that it won't do that now. Huh. So it's 0 now, but then when we put the wayboat on it, it doesn't do that. Huh. Yeah, I mean, you could, unlike the other labs we've done, you could always refresh this one because it's not going to give you some random amounts of reagent or whatever. We're dealing with very specific reagents for a very specific reaction. So if it's still doing that, yeah, just hit refresh, and it should work again.
But I have a question. So if we refresh
there
it,
it goes.
would it have a different like values and stuff?
No, be exactly the same.
Okay, thank
Yeah.
you.
Yeah. No, it's not going to give you like some weird concentration. Like now you've got 0.386 molar and like, now I got to figure that out. No, it'll be all the same.
Professor, for post-lab question, question number 2, explain how your results are illustrate of Hess law. What do you mean?
Exactly that. Explain how your results, explain how Hess's law helps you figure out what your results were. Did you do a demonstration of Hess's law? Explain.
And if I do the experiment in the real lab, what's the issue that I'm gonna face?
Yeah, what do you think would be the issues? Like here, I mean, everything works perfectly. What would be some sources of error, do you think? So just imagine what some sources of error would be. Would they be determining the masses? Would they be measuring the volumes? Would they be determining the temperatures? I mean, what do you think would be like the biggest problems getting really precise answers?
Temperature?
No, write it in your report. I'm not going to tell you.
Okay. So I have to answer based on my understand, correct?
You have to answer what?
Based on my understanding.
Yes, exactly. Precisely, yes.
Professor, I have a question. So for reaction 1 and reaction 2, are we just going to use like 50 ml of the solution?
Use different amounts. Use different amounts. I think it suggests you use like twice as much the second time you go through.
Okay.
So like, 2 grams of NaOH, 100 mils of half molar.
Oh, okay.
Yeah.
Okay, thank you.
Yeah. Or 50% more, which it doesn't really matter. Just different amounts. Just basically what we want to see is you're able to figure out what delta H reaction means. So if you use different amounts and you still come out with the same delta H reaction, then you understand how to calculate it. If you don't, then there's something wrong. That's sort of what we're looking for.
So if I use 0.5 grams of NaOH, can I use 25 ml of the solution?
Should be able to.
Okay.
Or you could use the same amount, actually. It won't matter.
Okay.
Yep. Just don't use less than half, because that's why 1 gram is selected, because that basically is exactly the same, or approximately the same number of moles that are in 50 mils of a half molar solution of HCl. That's why 1 gram is chosen. So they match up. But if you add an excess of HCl, it won't matter to the determination, because the amount of hydroxide that's neutralized will be the same, regardless of whether you have twice as much HCl or 10 times as much HCl. It won't make any difference. You'll still get the same delta H reaction.
Thank you.
Yep.
Oh, I have one more question. So the lab report, we just have to add this one table, right?
And the usual things, your discussion, like
Yeah.
how you, the usual stuff. But yeah, that's the lab table for, there won't be a graph this time, if that's what you mean.
Yeah.
There's nothing to graph. I mean, it's all kind of static information.
Okay. Thank you.
Nothing changed over time or anything. Yeah.
Professor,
Yeah.
could you please upload this and the previous lab video to
Doing the best I can, man. I got
Okay.
that computer that all this stuff is on is dying. And so I try edit it and then it crashes. And so, I'm doing the best I can, man.
Okay, thank you.
That's why I got this new computer.
How many lab report do we have left?
This is it.
Oh, this is the last
the
one?
last one. Yep.
Oh, yeah.
Yay. Okay. And tomorrow will be the last recitation. So then next week's lab and recitation will be done doing like problems for a review.
Okay.
Yeah.
Thank you.
No worries.
So just to clarify, for this lab report, we have to answer pre-lab questions from the chem lab manual?
Yes.
Okay.
Yeah. I think it's page, what did I say? Pages 117 and 118. Yes, you'll have to actually read through the procedure of that lab because it's slightly different from this one. It deals with weak acids and strong acids. So to read through it, because one of the questions involves weak acids and strong acids.
Do I need to answer a question and that below reaction 3? There are 2 questions.
Huh?
On
Below reaction 3.
In the instruction.
Oh, yeah. Yeah, those should be in your discussion.
Okay.
Yeah. All right, I will see you at lecture tonight. We're going to finish off number 9 and do a little bit of 10. Okay? Get into molecular interactions, which explains pretty much all of chapter 9. Well, most of it anyway. All right, we'll see you then.
Thank you.
Thank you. Talk to you soon.